Hello everyone and welcome to another episode of Campus 101 exam series. Today we're going to be looking at elasticity. I want to tell you that in the last 10 years, I've seen these questions in the past question about 5 to 6 times in the last 10 years. So it is a very important topic and the questions are usually easy. And we're going to be looking at the areas of stress, strain and Young modulus. But before that, what is elasticity? This is a rubber band. Is on about 7 centimeters now, and I can extend it even up to 20 centimeters, and it will return back to its original limit. So what is elasticity? Turned out that elasticity is the ability of a substance to return to its original state, original size, after it has been deformed, after deformation. Right? So the ability of a substance, of a material to return to its original size, keyword original size after deformation, is regarded as elasticity. So some materials are elastic, such as plastic, like this, my rubber band here, is elastic, and they are very useful in normal life. So where does the physics come in? Alright, so this is how the physics come in, and I want you to pay close attention now so that you get elasticity once and for all. So we have a material, alright, so like my rubber band, alright, the size, the normal size of my material, let's say the normal length of my material is L0. Let's represent the length of my rubber band as L0, alright. When I apply a force, an extension E happens. Alright, so, and I've discovered that, and you have also discovered that the force I apply or the extension is determined by the force I apply. If I apply it so strong, you see my rubber band is so thin and so stretched, and if I apply a little force, so discovered that the extension, the increase in length that is produced in my rubber band is proportional to the force applied. And anytime you see a proportionality sign in mathematics, what does that tell you? It tells you that you can remove that proportionality sign by putting a constant. And the constant that we're going to be putting in this case is dependent on the kind of material. So what do I have here? I have K is equals to F, the force applied, is equals to K, which is the elasticity constant of the material, in this case my rubber band, multiplied by the extension produced. So this is where the physics come in. I need you to really have this formula stored in the front of your mind, not in the back, in the very front. What it means that if I want to make K the subject of the formula, I can just divide both sides by E, and then what I'll have is F over E is equals to KE over E. E cancels here. So what I'll have eventually is that K, the constant of my proportionality, my elasticity constant here, will be equal to F over E. E is my extension. And how do I get my extension? E is equals to L0, L1, the next length, the eventual length, minus what? L0, alright? L0. So K is equals to, and I hope you are still following me, the force divided by the extension. The extension is the increase in length. How do I get the increase in length? I subtract the final length from the initial length, alright? So final length, I've already told you, is L1. The original length is L0. Alright, so at this point I have my constant. So force we know is measured in what? Newtons. And length is measured in what? Meter. So the K, the unit of K is Newton per meter. And this can be written as Newton per meter. I need you to know this. So most times they'll give you a question that will require you to calculate one of the following. Let us deal with these three terms. What is stress in elasticity? What is stress in elasticity? But before I teach you stress, let me show you something, a very important graph that you need to see anytime we talk about elasticity. This is my graph. And in this graph, I want to look at the elastic properties of my rubber band. My rubber band, this is length, this is force applied. Alright, so my rubber band has a size, so it's not starting from 0, it has a size, so that's why this graph is starting here. So the more I improve my force, the more my rubber band increases in size. It increases up to a point. At this point, if I put more force, it doesn't go proportional anymore. My graph begins to bend. At this point, even if I put more force, begins to turn. And even when I get to this point, if I increase the force, it breaks. All right, so I'm plotting the length versus the force applied. At this point where it is still obeying a proportional law, I call this the proportionality limit. This point is the proportionality point or proportionality limit. This point at which all the elastic property of my rubber band is lost is known as the elastic limit. The elastic limit or the yield point, labeled in some topic in some textbook as the elastic limit or the yield point. This point at which it breaks when I add more force is regarded as the break point. Break point or fracture point. Fracture means to break, all right? So the break point. So I want us to have this graph at the back of our mind. The proportionality limit is the point at which, at this point, the extension is still obeying a proportionality. So the graph is still linear. At this point, it is still elastic, but it's no longer linearly proportional. At this point, I call it my elastic limit or my yield point. The point at which if I add any other force, it breaks is regarded as the break point of my graph. So now with this set in our mind, I want us to look at stress. What is stress? What is stress and what is strain? Maybe we should start from strain because strain is easier to understand. Now, strain is a ratio of length. Strain is the extension produced. So the difference between the final length and the original length divided by the original length of my material is strain. Strain. So strain, L1 minus L0 divided by L0 is strain. You know where this is coming from now. I said E is the extension. So L1 minus L0 over L0 equals to strain. I need you to understand this very clearly. The next thing we're going to be looking at is stress. And that's why I wanted us to look at strain before we look at stress. Now, what is stress? I know stress is what you are feeling right now that you're watching this video. You are having headache, you're having back pain, but that is not the stress in elasticity. I'm sorry you are stressed, but that is not the stress in elasticity. Stress in elasticity is defined as force per unit area. The force that I've applied to my material divided by the cross-sectional area of my rubber band is regarded as stress. The unit of force is what? Newtons. The unit of area is what? Meter square. So I can see that the unit of stress can be regarded as Newton per meter square or Newton meter square inverse. All right, so that is stress. All right, and what is Young modulus? Young modulus is defined in elasticity as, you need to know Young modulus. Young modulus is defined as stress over strain. I hope this spelling is correct. Stress over strain. I think the spelling is wrong. But Young modulus is divided as stress over strain. Now, remind me. Let me show you once and then I'll close it. What is stress? Exactly. Stress is force divided by area. Now, divided by mathematics. Strain. What is strain? Exactly. Strain is the extension divided by the original length. The extension divided by the original length. Now, something I did not tell you at the previous part was, what is the unit of strain? Length over length. So that's meter over meter, and meter cancels meter. So strain has no unit. Are we clear on that? Strain has no unit. And here we're talking about stress. We're saying stress is force over area divided by strain, extension over length. All right. So when we want to do this, this can also be written as force over area times, we invert it, LO over L1, LO over extension. If you don't know how this happened, you need to go and learn mathematics all afresh. And thank God, Campus 101 has a mathematics section, so you need to go and check out the mathematics section so that you get your board maths very correctly. So what we have here eventually is that force length over area E is equal to Young modulus. I know this calculation is looking complex. When your exam is not usually complicated, let me show you one question that came out some years ago in your exam. And here is the question. Simply put, I'll read it twice so that we can do it together. The question from our exam, from your exam some years ago was this: a rubber band was stretched to twice its length. Rubber band was stretched to twice its length. Calculate the strain. Isn't that just beautiful? Calculate the strain. Calculate the strain. So what is our, and that's the question. There are no values, no numbers involved in this question. This is the question and this is the end of the question. A rubber band was stretched to twice its length. Calculate the strain. I'm waiting for you. No, this is how we go about it. First, bring out the values that were given to you in the question. Let's say the original length of the rubber band is what? L0. And we said the final length, L1, was twice L0. So L1 is equals to what? 2 times L0. And they said we should calculate the strain. Alright, so now we know that the initial length is L0. And we know that the final length is 2 times L0. So now let us calculate the strain. We know the formula for strain is what? E over L. E over L. So now we can know that the original length is what? LO. What is the extension produced? 2LO. So, alright, twice its length. Twice its length, alright? So 2, this is the final length. So now we can find strain as, we can define strain as the extension produced. And the extension produced, don't forget, is LO minus L1 divided by what? Exactly, LO. But we know that L1 is 2LO. So we can say this is equal to, I'm running out of space. So let me just take a new sheet so that we follow. Follow me closely now. So we're here. Can you see? Yeah, you can see. All right. So we know that L1 is equal to 2LO, right? And we know that strain is equals to L1 minus LO over LO. All right. So this is 2LO, since we know that this was twice its final length. So this is 2LO minus LO over LO. 2LO minus LO is what? Exactly, 1LO. So we have LO over LO, and LO over LO is equals to 1. So the strain on this material is equals to 1. There is no unit. There is no unit. Strain has no unit. And then this is the final answer. Can you see how cheap it actually is? So in summary, let's take it from the top again. We started by saying that elasticity is the ability of a material to regain its original size after deformation. We looked at force applied being proportional to the extension produced, and we found out the constant of proportionality to be dependent on the material we're talking about. So the constant of elasticity for rubber band is different for that for example, a football. All right, and the unit for the constant of proportionality is what? Newton per meter. We also looked at strain as the extension produced divided by the original length of the material, and that can be seen here. We said strain has no units. We looked at stress, the stress produced in an elastic material as the force per unit area, and we said the force per unit area has a unit of what? Newton per meter square. We looked at Young modulus, and we said Young modulus is stress divided by strain, and the unit for Young modulus is also Newton per meter square. And then we looked at this question of a rubber band being stretched to twice its length, and we were told to calculate the strain. And when we did that, we discovered that the strain of that rubber band was 1. And we said since strain has no unit, our final answer is 1. So thank you very much for watching this edition, and we'll see you in the next videos. Share with your friends.